Hey everyone, welcome to Into Mind. Can we ever win a race against the speed of light in a complete vacuum? What would happen then? Sir Albert Einstein asked the same question at the age of 15. No one had the perfect answer at that point of time. But in 1905, Einstein published a paper with title on the electrodynamics of moving bodies. There he said, nothing can go faster than light. Well, let's see. Why can't we cross that cosmic speed limit? According to Newton's equation v equals to u plus at, if a body with an initial velocity u equals to 0 and we can provide a constant acceleration of a equal to 10 meter per second square and the final velocity v is the speed of light, then on the 348th day it should beat the speed of light. Then where is the problem? As it turns out, Newton's equations are solely based on Galilean transformation. Suppose you and your friend are at a bus stop at point O. A bus stops at point P. Distance between the bus and you both is x unit. Your friend walked a little distance ut with a velocity u for time t. Now his distance from the bus is x minus ut. That's simple representation of Galilean transformation. It works perfectly in our daily lives. But when you are traveling near the speed of light, things get tricky. Now you can't work with the Galilean transformation, and then Einstein's special relativity comes into play. Near the speed of light, some bizarre phenomena happens. Number 1, mass increase. Einstein said, the faster you move, the heavier you become. How much heavier? Before that, allow me to introduce you with the key ingredient of this recipe. Root over of 1 minus v square by c square. Here v is your velocity and c is the velocity of light. Obviously at low velocity it is equals to 1. So then it doesn't matter whether you divide something by 1 or multiply with that. It will be same, but at higher velocities it is the most significant figure. You have to divide the normal mass with that expression. So at the speed of 99% that of light, your mass will be increased by 610%. At the speed of 99.9% that of light, your mass will be increased by approximately 2140%. So, with the increment of speed, mass increases exponentially and more force is needed to accelerate any body, and it becomes harder and harder to reach the speed of light. According to Maxwell's equation, no matter what your speed or reference frame is, light will always travel with the same speed from everyone's perspective. Well, it is a quite strange conclusion. Suppose you and your sister perform an experiment. The base of your experiment is an equation. Speed of light equals to distance by time. At first, to measure the speed of light, you take a back seat in a stationary bus. You know the length of the bus and light up a torch in the forward direction. Your sister stays outside and calculate the time light takes to hit the front of the bus accurately. You put those data in this equation and find exact speed of light. Again, you guys are ready to do the same experiment on a moving bus. After the experiment, you put your data. You see the speed of light is exactly same as before. But because the light has to travel a little more distance because the bus itself is moving, it could only be possible either if the time ticks slower in the bus or the length of the bus gets shorter to counterbalance the extended distance. You cannot feel it because everything including your thoughts and heartbeat gets slower then. But the slow time is not enough. That means the length of the bus is also get shortened. Now it is perfectly fit in our equation. Then the question arises that how much length gets shortened or how much time slows down. Let's get back to the term root over of 1 minus v square by c square. According to relativity, your new length will be your initial length multiplied by this term. Actually, this length contraction was first proposed by Hendrik Lorentz, and Einstein took that idea from his theory. Now let's tackle time. So your experimented time will be time for the outsider divided by this. Those are the second and third bizarre phenomena. From those three equations, you can certainly say that if you are traveling with the speed of light, your mass and time will be infinite and your length will be 0. Well, we can't break the speed of light, but the fabric of space-time can. And it is not violating the theory of relativity because it is not moving at all. Actually, it is expanding with an acceleration. And one day, the speed of expansion will be faster than light. And light from the galaxies and stars will not be able to reach us. So next time, when you will be stargazing, remember one thing. The beauty you are seeing now, our long descendants can never feel.